Welcome to the unveiling of Colonel James Hartman's revolutionary lenticular saucer, a 30 by 16 craft designed to pioneer the next era of propulsion. This project stands apart from previous lineages like AUREA and VIRELIO, marking a bold new chapter in advanced vehicle engineering. Today, we'll explore its transparent schematics, internal subsystems, and the groundbreaking teleparallel gravity bosonic modulation propulsion system. Every detail is attributed to Colonel Hartman, with the date of original conception, October 26, 2025, proudly displayed. Let's embark on a journey through the vessel's architecture, operational logic, and the science that could redefine our understanding of flight, buoyancy, and space travel. The transparent schematic reveals both the internal subsystems and the external hull architecture of the lenticular vessel. Every component is clearly labeled, with directional force vectors illustrating lift, buoyancy, repulsion, and thrust. This visual not only showcases the vessel's complexity, but also its elegant integration of advanced propulsion and structural systems. The schematic serves as a foundational reference for further technical overlays, subsystem blueprints, and propulsion reports. With Colonel Hartman's name and the date inscribed, this schematic marks the formal beginning of a new technological lineage, distinct from any previous projects. The subsystem overlay blueprint provides both top-down and side cutaway views of the saucer, meticulously labeling each module. This blueprint is essential for understanding the spatial arrangement and interconnectivity of the craft's propulsion, energy, and control systems. It highlights the modular design philosophy, ensuring redundancy and balance throughout the vessel. The overlay is not just a technical map, it's a testament to the craft's adaptability and readiness for multi-environment operations. With every subsystem documented, the blueprint lays the groundwork for deeper dives into materials, energy integration, and AI control. Materials and energy integration sheet details the multi-layered hull composition and the strategic placement of energy cores. The outer shell is crafted from a titanium aluminum lithium alloy, offering lightweight strength and corrosion resistance. The mid-layer utilizes carbon nanotube-reinforced polymer for impact absorption, while the inner layer features shape memory alloy for adaptive morphing. Thermal buffers and radiation shields ensure internal stability and protection. Energy is stored in solid-state lithium-ion battery banks and centrally mounted nuclear battery core, both shielded for safety and efficiency. This integration is vital for the vessel's resilience and operational longevity. Energy management is at the heart of the saucer's operational capability. Ion battery banks are located in the lower midsection, serving dual purposes of energy storage and hull reinforcement. The nuclear battery core, shielded with boron polymer and aerogel layers, is centrally mounted beneath the AI control dome. This configuration ensures direct energy feed into amplifier systems and field modulators, supporting both propulsion and onboard systems. The careful placement and integration of these energy sources are crucial for maintaining balance, safety, and uninterrupted power delivery during multi-environment missions. Amplifiers and field modulators are the technological backbone of the propulsion system. The amplifiers, arranged in a triangular grid beneath the battery cores, convert stored energy into torsion field pulses and bosonic ripples. These pulses are tunable via AI for precise phasing, timing, and directional thrust. Field modulators, ringed around the hull perimeter, control buoyancy, repulsion, and draw forces through teleparallel torsion tuning. This sophisticated network allows the craft to adapt dynamically to changing environments, ensuring optimal lift, stability, and maneuverability at all times. AI control systems are designed for seamless multi-environment flight. The ARK-AVACORE module manages atmospheric navigation, adjusting field phasing for altitude and predicting turbulence. The ARK-AQUACORE kit enables underwater operation, using sonar mapping and buoyancy monitoring for precise control. For space missions, the ARK-ANTICORE interchain handles astronavigation, zero-G maneuvering, and radiation shielding. Each AI module is tailored for its environment, ensuring the craft can transition smoothly from ocean depths to outer space, always adapting in real time to environmental changes and mission demands. In the air, the ARK-AVACORE navigation system provides modular autonomy for sky and atmospheric flight. It leverages teleparallel lift modulation to adjust field phasing, ensuring stable altitude control. The turbulence prediction engine allows the craft to adapt instantly to changing weather and wind conditions, rerouting flight paths as needed. This AI-driven approach not only enhances safety, but also maximizes efficiency, making the saucer highly responsive and capable of navigating complex atmospheric environments with ease. For aquatic environments, the ARK-AQUACORE exchange equips the vessel with a multi-fluid AI kit. This system uses sonar mapping for terrain and object detection, while buoyancy monitoring adjusts internal field density for precise float or sink control. Hydrodynamic stabilization ensures the craft remains balanced and efficient, even in strong currents. These capabilities enable the saucer to operate in rivers, lakes, and deep oceanic settings, maintaining full control and adaptability regardless of the water's challenges. In space, the ARK-ANTICORE interchange takes command. This astronavigation AI is preloaded with mission parameters for the Moon, Mars, and asteroids. It manages zero-G maneuvering through inertia-based vectoring and field propulsion, while also coordinating radiation shielding in response to solar activity. The system's ability to adapt to orbital mechanics ensures safe and efficient travel beyond Earth, making the saucer a true multi-environment vehicle capable of interplanetary missions. The Cutaway propulsion force diagram illustrates how amplifiers, torsion fields, and bosonic tuning layers interact dynamically. Amplifiers convert nuclear and ion energy into torsion pulses, which are visualized as blue curved vectors rising from the core. Above these, the bosonic tuning layer emits orange waveforms, phase shifted to create ripples, repulsion, or draw forces. The diagram highlights the upward propulsion force generated by synchronized torsion and bosonic phasing, with energy flowing from battery inputs through amplifiers and into the propulsion vector. This visualization is key to understanding the craft's unique lift and thrust mechanisms. Force dynamics within the saucer are governed by the interplay of torsion and bosonic fields. Upward propulsion is achieved through the precise synchronization of these fields, with adjustable phasing zones controlled by AI. The energy flow paths are meticulously routed from the batteries to the amplifiers, then into the torsion fields and bosonic layers, ultimately producing the desired propulsion vector. This dynamic system allows for real-time tuning of lift, buoyancy, and repulsion, adapting instantly to environmental changes and mission requirements. The Modular Core Operational Integration Chart formalizes the internal logic and subsystem interconnectivity of the lenticular craft. It covers propulsion telemetry, AI flight control, environmental adaptation, and positive force amplification. Each module is designed for redundancy and seamless exchange, ensuring the vessel can transition smoothly between environments. The integration of neural autonomy, real-time fluid dynamics analysis, and universal modular persistence makes this craft a model of operational resilience and adaptability. Propulsion Telemetry System employs fourth-generation field modulation with AI loop analysis. It continuously monitors torsion phase timing, boson tuning frequency, and lift metrics across fluid, atmospheric, and vacuum domains. This real-time feedback enables the craft to maintain optimal propulsion and stability, regardless of the operational environment. The telemetry system is a critical component for ensuring safe, efficient, and adaptive flight throughout every phase of a mission. The AI flight control system features a teleparallel gravity navigation module, capable of managing draw and repulsion forces through vector field dynamics. It adjusts buoyancy levels by inflecting frequencies, allowing for intermittent flotation and deep dives. The system also enables seamless transitions between space and oceanic depths, up to 50,700 meters. This advanced AI ensures the craft can adapt to any environment, maintaining stability and control at all times. Flight simulation is powered by neural autonomy reinforcement training, enabling the AI to learn and adapt across sky, river, ocean, and space environments. This matrix-based learning approach ensures the vessel can handle unexpected challenges, optimize performance, and continuously improve its operational protocols. The integration of advanced simulation and AI learning is key to the craft's versatility and mission success. Environmental adaptation is achieved through real-time fluid dynamics analysis, atmospheric and solar activity prediction, and coordinated thermal balancing and radiation shielding. The AI continuously monitors and adjusts the vessel's systems to maintain optimal performance and safety, regardless of external conditions. This proactive approach ensures the craft remains resilient and responsive in the face of environmental challenges. The Subsystem Exchange Module provides universal modular persistence, allowing the AI control module to ballot with redundant fallback systems. This ensures continuous oversight of power, propulsion, and lift layer integrity. The design prioritizes reliability and operational continuity, making the vessel robust against subsystem failures or unexpected disruptions during missions. The Condition and Tracking Dashboard coordinates power levels, checks hull integrity, monitors radiation shielding, and tracks navigation and environmental parameters. This centralized dashboard gives both the AI and pilot real-time situational awareness, enabling quick responses to any anomalies or threats. It's a vital tool for maintaining mission safety and operational efficiency. Autonomous system services include buoyancy tuning, field phasing, oceanic radar for underwater obstacles, and inertial frame referencing for orbital maneuvers. These services operate continuously in the background, ensuring the vessel can adapt to changing conditions and maintain optimal performance without direct human intervention. The integration of these autonomous functions is key to the craft's advanced operational capabilities. Positive force amplification is achieved through the layering of torsion and bosonic interactions. The AI dynamically tunes vector field phasing and resonance control, routing power as needed to maintain optimal propulsion. This system allows for real-time adjustments to lift, thrust, and stability, ensuring the craft can respond instantly to mission demands and environmental changes. The operational documentation sheet consolidates all core systems and logic into a single, comprehensive reference. It preserves the saucer's shape, with every subsystem labeled and integrated into the internal architecture. The report details the AI flight control tower, amplifiers, energy sources, hull composition, and subsystem logic. Mission parameters, including flight modes, depth capability, and thrust vectoring, are clearly outlined. This documentation is essential for both archival purposes and future operational planning. Internal Systems Overview highlights the central AI flight control tower, amplifiers for propulsion, dual energy sources, and a multi-layered hull. 8 operational modules are distributed radially for balance and redundancy. This arrangement ensures that the vessel remains stable and operationally resilient, even in the event of subsystem failures. The overview provides a clear understanding of how each component contributes to the craft's overall performance. Mission parameters include atmospheric, oceanic, orbital, and deep space flight modes, with depth capability up to 50,700 meters submerged. Lift and buoyancy are tuned via torsion phase timing and bosonic ripple modulation, while thrust vectoring is achieved through phased field layering. Subsystem logic encompasses telemetry, environmental adaptation, system exchange, and positive force amplification, ensuring the vessel is prepared for any operational scenario. Teleparallel gravity redefines our understanding of gravitational forces. Unlike general relativity, which describes gravity through spacetime curvature, teleparallel gravity uses torsion, a twisting of spacetime vectors. This is encoded in the tetrad field, allowing gravity to be manipulated as a force from torsional deformation. By dynamically modulating the torsion tensor, the craft can generate lift, repulsion, or neutral buoyancy, opening new possibilities for propulsion and maneuvering. The mathematical foundation of teleparallel gravity involves the torsion tensor and teleparallel connection. The torsion tensor captures the twisting of spacetime, while the teleparallel connection integrates this effect into the vessel's control systems. These equations allow for localized control of gravitational effects, making them ideal for advanced propulsion. By engineering the tetrad fields and their derivatives, artificial torsion fields can be created and modulated in real time. Sonic field modulation leverages force-carrying particles, such as gravitons or scalar bosons, to ripple spacetime. By tuning the frequency and amplitude of these bosonic fields, the craft can amplify or suppress gravitational effects. The AI layers these fields around the hull, phasing them to create constructive or destructive interference with torsion vectors. This interaction is key to producing thrust, lift, or inertial cancellation, enabling the vessel's unique propulsion capability. Quantum field equations, such as the Klein-Gordon equation for scalar bosons, underpin the vessel's bosonic field modulation. Wave function modulation allows the AI to control the phase and amplitude of bosonic fields, creating ripples that interact with torsion vectors. This precise control enables the craft to achieve a wide range of propulsion effects, from gentle lift to rapid acceleration or inertial cancellation. Torque field interaction is the core mechanism behind the craft's propulsion. Amplifiers convert energy into torsion pulses and bosonic ripples, which interact in a torque field to generate directional force. The field gradient force and lift modulation equations describe how these interactions produce dynamic, tunable lift and thrust. By adjusting bosonic phase timing, torsion vector alignment, and energy input, the vessel can adapt its propulsion to any environment. Antigravity in this context is achieved by decoupling torsion vectors from local gravitational wells and phase-shifting bosonic fields. This allows the craft to hover, float, or repel from planetary surfaces without traditional thrust. The process involves torsion field cancellation and redirection, accomplished through precise quantum modulation. This is not science fiction, but a sophisticated application of advanced physics and engineering. In ocean environments, the craft operates in flotation mode. Torsion fields are tuned to match fluid density, while bosonic phasing is minimized to reduce ripple interference. Lateral draw forces allow the vessel to hover or submerge without traditional thrust. The field resonance is characterized by low-frequency torsion pulses, with buoyancy controlled via phase inflection. This mode is ideal for river, lake, and deep oceanic descent. In the atmosphere, the craft enters hover and lift mode. Torsion fields are phased upward in concentric rings, while bosonic ripples are tuned to counteract gravity. The AI continuously adjusts resonance to account for weather and turbulence, ensuring stable hover and agile maneuvering. Field resonance in this mode features mid-frequency oscillations, with draw and repel forces dynamically balanced for optimal performance. At higher altitudes, the craft utilizes oscillating torque mode. Torsion fields rotate in phased loops, while bosonic layers ripple outward to stabilize lift. This mode is ideal for mountain flyovers and stratospheric glide, with high-frequency torque pulses and A-controlled phasing ensuring smooth altitude transitions. The vessel's ability to adapt its resonance profile is key to maintaining stability and efficiency at all elevations. In the vacuum of space, the craft operates in boson resonance mode. Torsion fields are decoupled from planetary wells, and bosonic phasing is amplified for inertial vectoring. The AI routes energy to propulsion nodes for zero-G maneuvering, with quantum-level ripple control and resonance tuned to orbital mechanics. This enables the vessel to navigate the Moon, Mars, and asteroids with precision and efficiency. Mission trajectory begins with ocean submersion. In flotation mode, torsion fields are tuned to match fluid density, and bosonic phasing is minimized for ripple suppression. The craft can reach depths of up to 50,700 meters, with the AI monitoring buoyancy and sonar mapping for safe navigation. This phase demonstrates the vessel's adaptability and resilience in challenging underwater environments. As the craft ascends, it transitions into atmospheric phasing. Torsion vectors are phased upward in concentric rings, while bosonic ripples counteract gravity. The AI adjusts resonance in response to weather and turbulence, ensuring a smooth ascent through the atmosphere. This phase covers altitudes from ground level up to 12,000 meters, showcasing the vessel's ability to maintain stability and control during rapid environmental changes. During altitude transfer, the craft employs propulsive force mode. Oscillating torque fields stabilize the ascent, while bosonic layers ripple outward for lift modulation. The AI routes energy to amplifiers for precise thrust vectoring, enabling smooth transitions from 12,000 to 80,000 meters. This phase is critical for reaching the upper atmosphere and preparing for space entry. In space vectoring mode, torsion fields are decoupled from planetary wells, and bosonic phasing is amplified for inertial navigation. The AI engages orbital protocols and coordinate shielding, enabling the craft to navigate the Moon, Mars, and asteroids. This phase demonstrates the vessel's capability for interplanetary missions, leveraging advanced field resonance and propulsion control. The command interface schematic details how the pilot or AI interacts with all major systems in real time. The central console displays torsion and boson amplification waveforms, with manual override options via neural joystick or holographic slider. Buoyancy levels, torque vector monitoring, obstacle mapping, thermal balance, and orbital phasing are all accessible through intuitive panels. The AI status and system exchange panel provides real-time feedback on subsystem routing and power flow, ensuring seamless control and operational awareness. The central console layout features real-time waveform feedback for torsion and boson amplification, A-controlled phasing overlays, and manual override capabilities. Buoyancy levels can be adjusted via touch panel or voice command, while torque vector monitoring aids in altitude transitions and orbital maneuvering. Obstacle map radar integrates sonar and LiDAR data, highlighting terrain and hazards for safe navigation. Thermal balance and radiation shielding are managed through dedicated panels, with the AI coordinating shielding layers and hull modulation. Emergency overrides are available for critical situations, ensuring the vessel remains safe and operational even in extreme environments. This system is vital for long-duration missions and deep space travel. Orbital oscillation phasing controls resonance timing for zero-G vectoring, displaying frequency and spatial coordinates in real time. The AI synchronizes with planetary motion and gravitational wells, ensuring precise maneuvering during orbital operations. This advanced control is essential for interplanetary travel and complex mission profiles. The AI status and system exchange panel displays subsystem routing, fallback logic, and power flow. An AI online indicator confirms active control, while the pilot can balance subsystem priorities or initiate manual reroute as needed. This interface ensures both human and AI operators maintain full situational awareness and control at all times. The Technological Feasibility Report evaluates each component of the teleparallel gravity bosonic modulation propulsion system. Teleparallel gravity is theoretically sound, with bosonic field modulation partially demonstrated in current research. Torsion field amplifiers remain conceptual, requiring breakthroughs in artificial spacetime engineering. A-controlled phasing, energy systems, and hull materials are all feasible with today's technology. The report concludes that while full realization depends on future advances, a prototype with simulated field layers and AI control is possible now. Gravity control is achieved by engineering tetrad fields and modulating their derivatives to create artificial torsion fields. Bosons are extracted via high-energy field interactions, with amplifiers synchronizing bosonic waveforms for selective lift, repulsion, or buoyancy. AI systems monitor real-time feedback, routing energy from batteries to amplifiers, which emit torsion pulses and bosonic ripples in phased layers. This approach enables the vessel to manipulate gravity locally, paving the way for advanced propulsion and maneuvering.